Hey everybody, look at these 3 questions. Which of these is bigger? Okay? By the end of the video, you're going to be able to answer this question in about 2 seconds. This is really one of my favourite problems of all time. Let's get into it. Hey everybody, welcome back to Mad Maths. Today we're going to be considering one of my favourite problems of all time is what's bigger, a to the b or b to the a? Right, so I've just written that here. We have a to the b is greater than b to the a, or a to the b is less than or equal to b to the a. I'm just going to write these inequality symbols at the same time, just so it's a bit neater, but obviously this is equivalent to saying what's bigger, a to the b or b to the a. Okay, so let's consider this. Right, we have powers, but these powers are causing issues for us, so it'd be nice to introduce the natural logarithm. However, we're working with inequalities, okay? So just before I do that, let me just draw the graph of the natural log. So this is the natural logarithm of x, okay? And we see that the natural logarithm of x is a strictly increasing function, and that means if we take the natural logs of both sides, it's not going to flip the inequality signs, so we don't need to worry about that. So we just take the natural logarithm of both sides, and here we have a to the b and b to the a. Okay, and that's why we introduced the logarithm in the first place, so we can bring down those powers. Okay, so now I still have the natural logarithm, but I can bring down that b, and I can bring down the a on the right hand side. Okay, and now let's just isolate a and let's isolate b. So divide both sides by ab, and I'm going to get, I still have the natural logarithm. Okay, but on the right hand side I've divided by a and I've divided by b, and on the left hand side I've divided by a and I've divided by b. So we have this statement, okay? If this is, so for example, if the natural logarithm of a divided by a is greater than the natural logarithm of b over b, then this is the same thing as saying that a to the b is greater than b to the a. Okay, so if we can consider this statement, we can learn about this statement, because these are equivalent things. Okay, so we need to consider the graph of the natural logarithm of x divided by x. Okay, so consider the natural logarithm of x over x. Okay, and I'm just going to let this equal y. Okay, and to better understand this, we want to graph it, and in order to graph it, we need to know its derivative and also the limits as it goes to infinity and as it goes to the origin. So just note, we have something of the form. U over v, where u and v are both functions of x. Okay, and we want to consider the derivative. Okay, well, we have a nice formula for the derivative of a quotient. Here's a reminder of the quotient rule. So let's apply that here. So we have y dash is equal to v times the differential of the natural logarithm of x, which is just 1 over x. We have x times 1 over x minus u, which is this guy, times the differential of x, which is just 1. So just times by 1 here. And then divide the full thing by v squared, which is x squared. Okay, just neaten this up. We have 1 minus the natural logarithm of x over x squared. And we want to consider, when is this 0? Right? So this is 0 if and only if the top thing is 0. So we have 1 minus the natural logarithm of x equals 0. Okay, well this means that 1 equals the natural logarithm of x, which is equivalent to x equals e. Okay, so we have a stationary point at x equals e. Okay, well let's consider the nature of the derivative when x is bigger than e and when x is less than e. Okay, so when x is bigger than e, the natural logarithm of x, so e is here for example, and here's 1. Okay, when x is bigger than e, the natural logarithm of x is bigger than 1. Okay, so we have 1 minus something that's bigger than 1. Okay, so when x is greater than e, it's clear that this thing is going to be negative, so y dash is less than 0. Okay, now consider when x is smaller than e. Okay, so go back to the graph. Okay, when x is less than e, we have that the natural logarithm of x is less than 1. Okay, so this thing is going to be 1 minus something which is less than 1. Okay, which means the top thing's positive, and of course x squared is positive as well. So we have positive over positive, which is positive. So when x is less than e, y dash is greater than 0. Okay, and at x equals e, it is 0. Okay, so we know we have a single hump like this, a single stationary point, and we don't know quite yet what happens as x goes to infinity or as x goes close to the origin, but we have this hump. Okay, that's good, we're almost there. So, let's just consider the limit as x goes to 0 of the natural logarithm of x over x. Okay, well, if you consider the graph, okay, as natural logarithm of x goes to 0, it goes to minus infinity. And as x goes to 0 from the right, okay, well, it's going to go to 0 from the right. So we have something which is of the form minus infinity over positive 0. Okay, so this is of the form minus infinity over 0. Okay, and this means that this thing is going to blow up to minus infinity. Okay, when we divide by 0, things are getting bigger. Okay, and minus infinity divided by positive 0 is going to be minus infinity. Of course, that's not entirely rigorous. Okay, however, you could bound this, you could say that this is, okay, so if you want to be a bit more rigorous, you can say that the natural logarithm of x is going to be less than or equal to minus 1 for sufficiently small x. Okay, and then consider whether minus 1 over x, consider the limit as x goes to 0 of minus 1 over x, and you can see that that diverges to minus infinity, and as the natural logarithm of x is less than minus 1, well then the natural logarithm of x over x also diverges to minus infinity. So if you want to be a bit more rigorous, you can do that, but you know, I don't want to spend too long on this, so I'm just going to say that this is minus infinity. Okay? Now, something that's slightly more rigorous is when x goes to infinity of the natural logarithm of x divided by x. And for this one, we have something of the form infinity over infinity. So we can apply our favourite rule, the easiest rule, L'Hopital's own rule. So this is equal to the limit as x goes to infinity of the differential of these things, okay? So the differential of the top thing is 1 over x. The differential of x on the bottom is just 1. So we're considering the limit as x goes to infinity of 1 over x, which is 0. Okay? So, I'm just going to rub some things off and collate this information at the top, and I will be back in a moment. Welcome back everyone. Now we get on to the exciting part of the video. We have all the necessary ingredients to graph y equals the natural log of x over x. So let's get into that. So y goes to negative infinity as x goes to 0. Then we have a stationary point, and then the gradient is negative after x equals e, and it goes off, so y goes to 0. Okay, this gradient here is negative, and this gradient past e is positive. So here's x equals e, and that's all the information we need to know. Okay, so now get my blue and red pens. If a is bigger than e, okay, and b was said to be bigger than a, so b's here, then the natural logarithm of a over a is bigger than the natural logarithm of b over b. And if we look here, this is equivalent to saying a to the b is bigger than b to the a. Okay, so if a is bigger than e, then the smaller thing raised to the bigger power is bigger. Let's look at our examples. Okay, so 21, is that bigger than e? Bigger than or equal to e? Yes, it is. So this one's bigger. E, is e bigger than or equal to e? Yes, it is. Therefore, this one's bigger. So for our final example, we have the square root of 2 raised to the power of square root of 3. Both of those things are less than 2, which is less than e. So we're on the left side of e. Okay, so let's rub these out really quickly. Okay, so now we're considering the graph to the left of e, and this is when the gradient is positive. Okay, it's positive and it's continuous. Therefore, a is here, and let's have b to be here. We see that the natural logarithm of b over b is bigger than the natural logarithm of a over a, which implies that the natural logarithm of b over b is bigger than the... I've just repeated the same thing, that's not what I meant. This implies that b to the a is bigger than a to the b. Okay, so for this example, it turns out that this one is going to be bigger. Okay, and we know that straight away just by considering whether the numbers are bigger than e. That's why it's one of my favourite problems. When you first look at it, it kind of looks like a number theory problem, even though no one said it only involves integers. But it doesn't look like you'd use calculus straight away, at least that's not what I thought of. But yeah, it's a really, really cool solution. I really enjoy this problem. So if you enjoy this problem too, then subscribe, look out for more. I'm going to be doing many more cool problems like this. And yeah, I'll see you guys next time. Thank you.
Yo guys, subscribe to Madman.